Yeah, we can start now.
Okay, you guys ready to get started? All right.
Well, let me. Okay, so we're gonna have the journal club first, and then we'll talk about the class stuff. So go ahead, JJ Campbell, who's on distance learning, dislocated shoulder,
Yep.
but he came into class.
Yep, exactly. So my partner was Tom Sahota. He's also in distance learning. So I was discussing with Dr. Hu about, doing our project about the natural gas industry. So we decided to do that as a topic instead of like an actual article. So because I work in the natural gas industry, so I'm going to explain a little bit about my job in the natural gas industry. So I'm in system planning. So the job is fairly self-descriptive. So I plan out the system. So my company is in Massachusetts. It's called Berkshire Natural Gas, and we're in charge of about 3 counties. We distribute gas to Berkshire County, Franklin County, and Hampshire County. And during our peak demand, we can supply about 1 gigawatt of power over about 1,600 square miles.
During a mechanical failure of the worker regulator, the monitor regulator will begin to take control. In many cases, natural gas heaters are installed upstream of the gate station to maintain a minimum gas temperature. This is required so that when gas flows or usage is high, the natural gas temperature can stay high enough not to freeze the valve to terminal. The maximum allowable operating pressure is the maximum pressure that a system can operate. Operating above this pressure can result in catastrophic failure of the mechanical equipment. Therefore, pressure regulators are used to control the system pressure. If the pressure regulator fails, monitor regulators are placed in the line and sized appropriately to relieve the system and prevent catastrophic failure. Pressure tests are required after construction prior to initial operation to ensure the integrity of the piping system is intact. In emergency situation, the system pressures can reach a maximum of only 10% above the maximum allowable operating pressure. During normal operations, the regulators are set below the maximum allowable operating pressure to ensure the safety of the system. There's also a minimum required operating pressure, and that's typically set at about 50% of the maximum allowable operating pressure. This gives the system plenty of room to fluctuate pressure during normal operating scenarios. In the graphic below, you can see a typical layout of the different pressure ratings on the gas distribution system. The 750 psi supply can be split into a 60 or 40 psi distribution, which are controlled by a series of strategically sized and placed regulators. Ultimately, both systems are reduced down to a manageable pressure rating that is usable by the end customer. This slide discusses how a simple, internally operated pressure regulator functions. The purpose of a pressure regulator is to maintain some downstream set pressure. Therefore, the valve will operate according to the feedback given from a sensing line on the downstream pipe header. In the picture on the slide, the red line illustrates the inlet gas pressure, and the blue line represents the outlet gas pressure. When the sensing line pressure drops below the setting on the regulator, the pressure underneath the diaphragm will be less than the spring pressure in the yellow part of the figure. This causes the valve stem to drop and the plug to come off seat, allowing more gas from the red line to enter into the cavity of the valve, making its way into the blue section, or the outlet of the regulator. In order to increase or decrease the set point of the regulator, you can adjust the adjustment screw either clockwise to decrease the outlet pressure or counterclockwise to increase the outlet pressure. This is a basic regulator. Some systems include pilot regulators. Either way, the concept is similar for both applications, and the objective is to ensure that your pressure regulator is set correctly in order to reliably maintain a downstream pressure for its users.
Okay, so that's a little bit of introduction about, the various levels of the system. So one thing that I work on in my job, and basically one of our main objectives, is replacing the low pressure systems. So typically, if you imagine this is like a top-down view, and each one of these lines represents a whole street, and a square would represent like a city block. And typically, this is the way it's represented, different colored lines on a white background. So this would be like a low pressure system, and the low pressure systems operate at 10 inches water column. So we're interested in replacing these because they're kind of like a remnant of the beginnings of the gas industry from like over 100 years ago, and a lot of them are made with like cast iron. So basically one of our objectives is to go in and replace everything with plastic. And it's also industry best practice is to replace these 10-inch water column systems and put them on something like 40 or 60 PSI systems. So the way that we do that is, first, we're going to come in and we're going to parallel part of the system with our intermediate pressure, which is the green line. And then we're going to have an intermediate pressure and a low pressure pipe on the same street. So then we can go around to all the customers in this area, and we can move them over to the intermediate pressure main. And that takes a while, so it's good to have both of them and not just like do it all at once. So once we get all the customers transferred over, then we can, cut off this section here of the low pressure system, and then we're going to purge out all the gas, and then basically we just abandon that pipe there. So you have to be careful here because, as you can see, previously the low pressure system had 2 feeds, but now it's only got 1 feed. So now you got to make sure that it's still going to work, and you also have to make sure that there's enough pressure in this intermediate pressure system to be able to supply this additional load. Another thing that we work on is making sure that these regulators have adequate inlet pressure. So these red lines typically represent like 100 or 200 PSI system. And so what we need to do is make sure that there's enough inlet pressure. So we need about a 15 PSI difference between the inlet and the outlet pressure. So for a 60 PSI system, we need to have 75 PSI at the inlet, or 70 or 75. So, I worked on a project recently where we had to replace 1 mile of 6-inch steel pipe with a mile of 12-inch plastic pipe to help increase the pressure a little bit because we weren't quite getting like that 75 that we wanted. And another kind of thing that we might work on is replacing regulator stations. So it's an example of a system that's fed by a low pressure system that's fed by 2 regulator stations. So every once in a while we do need to replace these regulator stations, and maybe they're getting old or something. So when that time comes, then you kind of need to think like, well, is this really the best place to put this regulator station, or should we put it somewhere else? Do we really want to put it right back in the same spot? So for example here, if you might want to bring one of these regulator stations that's right on the edge of the system here into the middle, especially since we already have an intermediate pressure main that's going through the middle. So you could just move it over to the middle and it would work better. Or you could consider maybe we could just get rid of it altogether, because the less moving parts there are, the better. So maybe the system can be supported by 1 regulator station now. So these are all considerations that we have to take into account when we're replacing these regulator stations.
1 more minute. 1 more minute.
Okay. Can I go like 3 minutes over?
Oh, Yeah, maybe 2 minutes.
Okay, all right, so this is a little bit about the units. Okay, so the heating degree day, basically it's what we use to plan out the system loads. So there's a linear relationship between the heating degree day and the energy usage. So basically the heating degree day is the average daily temperature subtracted from 65. So if the average daily temperature is 35 degrees, it would be a 30 heating degree day. And it turns out that the heating load is twice at a 60 heating degree day as that it is at a 30 heating degree day. So we calculate out these loads here. Basically, we sum up the total gas usage over a period, and then we subtract the base load, which is like hot water and cooking, and then we divide that by the total heating degree days in that period, and that will give us something like therms per heating degree day. And then we multiply that by our design day, which is like the day that we anticipate to be the coldest day of the year, which might be like a 70 heating degree day. So that will give us the total therms that we're going to use for heating on the peak day of the year. And then we add that to the base load, and the maximum hourly usage is about 5% of the daily usage. So the curtailment and peak shaving, this is a graph that represents how much gas we might use on various heating degree days. So at a certain point, we curtail a lot of our industrial customers, and the red line represents our maximum gas supply. So at a certain point, we have a contract with our industrial customers where we are going to shut them off for up to 15 days a year, and that will give us a little bit more gas supply to work with. But then eventually we are going to reach our maximum supply, and so then that means that we're going to have to activate our LNG and propane plants. So this is kind of what those look like. Basically, we just have a bunch of gas liquefied in these storage tanks, and then we vaporize it off. So the program that I use to solve all this is called Synergy Gas, and there's a lot of different equations that it can use to solve the pressure difference between 2 points. And we just use this fundamental with flow-dependent friction equation, which is just general gas equation for compressible flow in a pipe using the momentum equation. So that is the equation that we use between two nodes. And then typically, this is kind of how we build out our hydraulic models. So basically what we're going to do is we're going to bring all these customers on this street, on this half. We're going to bring all these customers, we're going to bring them over to this node. And so we get these nodal networks. And so we know what the gas usage is at each node, and we know what the upstream pressure is. And basically at that point, since there are so many loops, you have to use Kirchhoff's law. But in any city, there's hundreds of loops. So luckily we have computers that can help us out with that, because otherwise it would take like weeks and weeks. Okay. Sorry, it was a little bit over.
Okay. Do one or two questions.
Any questions?
So when you're going from the old iron pipe to your plastic, what did you say the change in diameter was to get the same flow? Increase the flow?
We don't really need to change the diameter too much. Typically, all the old cast iron pipes are like really large diameter, like 6 or 8 inches nominal diameter. But you could pretty much replace that with like a 4-inch or a 2-inch main, because the pressure is going to be a lot higher when you replace it. So you're replacing like an 8-inch pipe that flows at 10 inches of water column, which is really low pressure. So there's 27 inches water column in 1 psi. So that's really low pressure. So we're replacing that by something that is like 40 psi. So we can make the diameter much smaller.
You mentioned you're going to replace a steel pipe with a plastic one to increase the pressure.
Yeah. That was just because the diameter was going to be bigger, and typically, back when the steel pipe was made, it was put in like the 60s, so they used steel a lot more back then. But our standard practice these days is to use plastic for pretty much everything, just high-density polyethylene plastic mains. But if the pressure gets above 100 psi, then we have to use steel. So basically, anything 100 psi and below, we are going to try to use plastic. And so the reason it was going to increase the pressure is because we replaced a 6-inch main with a 12-inch main. So, and basically at that point, like the flow through the 6-inch main was so much that 6-inch just wasn't really doing the job.
But you said you're going from steel to plastic to increase the pressure.
Yeah.
But you said plastic, it takes lower pressure than steel.
Up to 100 psi. So that system was a 100 psi system. So the plastic can take up to 100 psi.
Okay, so it can take it as high if you're under 100 psi.
Yeah, it could. Yeah, plastic
way
and steel are equivalent under 100 psi, and generally plastic's a lot cheaper than steel is. So, and also it's more environmentally friendly too. So we always use plastic when we can, but there are some setbacks to the plastic because it has thicker wall thickness, so there's less inner diameter than the steel. But yeah, so up to 100 psi you can use plastic or steel. Over 100 psi you have to use steel.
All right, let's thank JJ again.
I meant like to increase the actual system pressure, not the maximum pressure.
Oh, okay.
Like, because.
Do you need help?
Yeah,
I got it for you. You got it? Here you go. Where are you sitting? You sure? Sure. All right, thanks a lot. All right. Who's up for next week?
I think I should be for next week.
You guys are sharing? Or maybe you have two. We can do Monday and Wednesday. That's fine. All right. So I've got office hours. So office hours today. I'll be in my office at 1:30. But I'm also teaching an undergraduate class, and I returned their first quiz today, so it might be a little chaotic. But I'll also be here Thursday and Friday, and if you want to have office hours in person, send me a note on the GroupMe, and I'll send you the times. Homework 1 is due Friday. So there's 20 people in person and there's 10 people online. I understand there's going to be some some people are basically pretty much done with homework, and then we have some poor folks who just Cedric, right? Mm-hmm. Cedric just added the class. So no matter how far behind you think you are, you're not more behind than Cedric, because this is his first lecture. You're a brave man. He actually we had to send a personal note to the registrar. Okay. So, Cedric, do you know anyone here? No, I do not. All right. Basically, there's a class GroupMe. You want to add yourself to the GroupMe. I will stick around until 11 a.m. Then the new class is going to come in. But maybe talk to Don. Talk to someone nice, and they will try to catch you up. This may not be a bad time to review like what we did, just because for the class and for you as well. So we've had 4 lectures. We're deriving the governing equations. So the governing equations, and we're deriving them in general for a fluid. And then we're going to look at them specifically for a Newtonian fluid. So some of the big ideas, we talked a little about the material derivative, which is the time derivative plus what we call the convective derivative. Anytime we're trying to follow a fluid particle, as it varies from point to point, for example, we'll do this in 2 ways. We'll follow the density of something, which is a function of space and time, or the velocity of a particle, which is a function of space and time, we're going to use a material derivative to do that. For example, this idea that something is incompressible, it comes from the definition of the material derivative. So this means incompressible. It means that doesn't mean, whoa, what's happening? Incompressibility doesn't mean that the density's constant at every spatial point. For example, I could have some fluid that has stratified fluid that has basically rho 1 here and rho 2 here, and let's say it's sloshing back and forth. Sloshing. That is still a incompressible fluid, clearly, right? I've got salt water on the bottom, but if I were to look at a single point, like I look at, I don't know, I put a little sensor there, that's going to read different densities because sometimes I'm going to have like the heavy salt water and sometimes I'm going to have the light salt water. But it's still incompressible because it says if we're following fluid particles with a material derivative, those fluid particles are maintaining the same density, that a particle cannot change density itself. And so because we're looking at fluids in motion, you need to have this material derivative. There's no getting around it. All right, so we spent the first lecture deriving conservation of mass. And by the way, Cedric, all these lectures are on Canvas under Media Gallery. And anyone else in the class, if you haven't known, that everything's recorded for the distance learning people.
And also, you can get his notes, what he's writing on the board now.
Yeah, that's on syllabus too. Yeah. All right, so conservation of mass. Basically, we showed it's we calculated to be this. Okay. Where basically we got some fluid flows going through here. We have some outward normal. And we took an integral and we reduced it down to do a point. Now, the first homework is not about fluid mechanics. The first homework is all about the basics for this course, which is index notation, and it's how to do quantities like this, where you have the divergence of a scalar quantity, which is a function of space and time, and u, which is a function of space and time. And this from index, so we basically had to, I guess it's fair to say we spent 2 weeks doing index notation. And a lot of you are going to spend the next 5 days doing index notation because the homeworks are going to be due. And we have the quiz. The homework is due on Friday, this Friday. But and I think I'll give you the solutions after I get all the homeworks. Yeah.
Do you know when the quiz is going to be on? Monday or Wednesday?
I wanted people to look at the solutions, and people wanted a chance to look at the solutions. So to be honest, maybe not even next week. It'll probably be the week after, because I can sense that there's going to be some late homeworks. Yeah.
But the quiz is still just going to be on the first homework.
Yeah. I only have a quiz on one homework, but I want to make sure everyone's on the same page before we do this. Before we do the quizzes. All right, so we use index notation to show quantities like this, that this is equal to u dot del rho plus rho del dot u, okay? Which would be really difficult to show without index notation. Okay, and then from that, basically using incompressibility, we showed that basically conservation of mass, from now on we're going to be using this. For both Newtonian and non-Newtonian fluids, this is for any fluid that basically the density does not change of a fluid particle. Okay. All right, so that was conservation of mass, and which was in some ways the easier part of the conservation equations. Then we derive conservation of linear momentum. All right. All right. Conservation of linear momentum, this is basically F equals ma for a fluid. The ma part's on the right because your fluid particle could be squeezing, could be shrinking, it could be stretching out, but it's not changing in mass. So we have the material derivative to follow the fluid particle. Then we have this body force, and we have surface forces. And this is where we started using tensors, because if you consider like a typical cube, for example, you've got x, y, z, which in our world, in our notation, we're using 1, 2, and 3. Each face, for example, I call this the positive one face, can have forces in the 2 direction, in the 3 direction, or the 1 direction. But because there are 3 positive faces, there are 9 different possible forces, 3 normal forces and 6 surface forces. That's why we need to introduce this tensor notation. Okay. And this is what we called the Cauchy momentum equation. And Cauchy brought in this idea of, hey, we've got 9 forces. Let's just write that as the divergence of this tensor, which has 9 components. Okay. All right, so that was linear momentum. And we were stuck with this idea of t, but we didn't have any information about t. So to get information about t, we had to do conservation of angular momentum. All right, conservation of angular momentum. Where we derive this. All right, so conservation of angular momentum, we're looking at the position away from some origin, and we'll call that position x. What version do I want to write? Let's write this version. It's easier to understand. So basically F equals ma on the left, where F is where ma cross with this x to give us the angular momentum. We've got basically the body force across the volume minus, and this is where again we use the index notation, minus plus t double dot dv. Okay. Where this big sigma is a triple tensor. So this has 9 components, 9 components. This has 27 components. And we will introduce an 81 component tensor by the end of the lecture. Great. But because it's symmetric, we'll have fewer components. Okay. Basically, from this, we showed that we showed a couple things. The stress tensor T is symmetric. That means symmetric matrices have 6 independent components, not 9. Okay. Okay. Specifically, you have the diagonal, and you have the elements above the diagonal. All right, and that's what we learned from conservation of angular momentum. All right, now we're getting close to where we are now. So we ended last time with these so we're going to spend the rest of the day talking about stress in basically a moving fluid. And last time we talked about the static case is the easiest to understand. The static case, basically, you have constant pressure in and had defined as outward. We said that basically, if you have no moving fluid, your pressure is just all normal. So I is this is the identity matrix. Okay, which is just 1s, 1, 1, 1 for a three-dimensional world. And this negative sign is because we consider pressure to be positive, like squeezing us inward. So we ended last time with the equation of fluid statics, which, you take the Cauchy momentum equation and you have no fluid motion, and you have this. And this pertains to the homework. Here we talked about if basically you just have gravity. So there's gravity. Then if you use T, the stress tensor just has pressure components, then what you have left is that rho g is equal to the gradient of the pressure. And physically, what that means that dp dx equals dp dy is equal to 0, and dp dz is equal to negative rho g. In other words, pressure constant on horizontal lines. It doesn't vary in horizontal lines, and pressure increases linearly as you go down in the fluid. This is pressure increases linearly with decreasing z. Okay. So when is fluid static? To answer that question, we talked a little bit last time. This is where one of these identities is useful. So this is this is Pascal's law. We'll call that star. So if you take the curl of star, let's just do that. We did a little too fast last time. Let's do it carefully this time. Everyone see if you can use your, so you should try to, the problem set 1 has all these identities. In office hours, you can save a lot of time if you actually try to use the identities, and you don't have to go to index notation world. So you could basically use them to try to calculate this thing. So everyone, if you've done your homework, try to use these identities to calculate what this should be. It should be 2 terms. And you just joined, so you can look at mine. Remember, rho is a scalar. G is a vector. Rho in particular is a function of space and time, and G is just a constant. Okay. So based on the identities, what 2 terms are you going to write? See if you can write down your paper and talk to your friend if you don't know. Yeah.
What's the thing right after the row at the left? Like row.
Oh, this is star.
Oh, this is star.
Yeah, this is Pascal's law.
Oh, okay.
I'm basically taking the cross, the the cross product of that. Okay, and and let's be complete. Del cross del P. Remember, this is pressure, and this is density. I try to write them differently. So using the identities, let's break down the left side and the right side. So del cross, the curl of a gradient, what is that equal to? Exactly right. That was Layla, right? And what equation is that on the sheet? Does anyone remember?
4.
No,
Wait,
4.
I'm sorry, for a vector?
It's one of the identities, right?
Yeah, it's 4.
4, Roman numeral 4.
Yeah, Roman numeral.
Okay. And that's something you can remember. Basically, the curl of a gradient of a. So the reason why you can actually calculate p, because p is a function of space and time, right? Curl of a gradient of anything is going to be 0. Now let's write the left-hand side using another identity. So you should basically, in some ways, this is like a product rule for grad students, plus del rho cross g. Right? It's exactly like the product rule, except you substitute the dots with these cross symbols. Okay, can I simplify this further? And what identity was this on the sheet? 4.2. So identity.
That brings up a real quick question.
Uh-huh.
My memory's crap. Are we going to have to memorize all these for the quiz?
I think I can give it to you, but I think the problem is you have to derive. Sometimes you'll have to derive them with index notation. And the goal is that we've done this derivation. You shouldn't have to derive them anymore in your life, unless you, for some reason, be a professor and you have to do it all the time. But otherwise, you can take those as fact. Except in the quiz when I ask you to show me why it's true. Otherwise, you can assume. And I'll give them to you if you need it. I'll give you the list of identities. Because the goal is not to memorize stuff, is to be able to use it when you need it. So can we simplify these two terms? Can we simplify any of these? Nabla, this is a spatial derivative, right? That's exactly right. So what does the left term equal to? Yeah. Because g is a constant vector. It doesn't depend on space, right? So we're left with the following. By taking the curl of the equation of motion, we're left with basically del rho cross g is equal to 0. Physically, what does that mean? That means we so this is for a static fluid. Because we assume that there's no velocities and the equation of pressure. The only thing that's, we have non-zero velocities. So that means that if the gravitational vector and the gradient of the density are not parallel, we get flow. And we call that convection. Let's draw out what that means. So let's consider the case when you should get a static fluid, our stratified fluid. So this is rho 1, rho 2. Again, gravity is going downward. Here, I've got an increasing, so this is a high density, rho 3. And this would be low density. If I were to draw my gradient of pressure, what direction should it be? Yeah. Pressure is it going up or down? Going towards the increasing value, right?
Oh, yeah.
I think down. Gradient pressure. Sorry, not gradient pressure, gradient density. So this is the gradient density. It's going down, and you can see, if I basically have like the ocean, like the people who study these oceanographers, the bottom of the ocean is actually way saltier than the top. And there, it's because you've got heavier fluid supporting the weight of lighter fluid. So this is happy. This is happy state. That means equilibrium. But what's not a happy state is if you have them perpendicular. For example, if you have a hot fluid, hot, and you have a cold fluid here, then you're going to have a low density here, low rho, and you're going to have a high density here, high rho. So my pressure gradient is going to be this way, del rho, and my gravity is going this way. Guess what's going to happen to this fluid? Yeah, you're going to get convection because let's see, it goes here and it's going to go. Let me see if I did that right. So it's going to go. Sorry, the other way. Basically, as it gets to this cold side, it's going to basically get cold, decrease in density, is going to fall, and then it's got nowhere to go when it falls, so it's going to go to the left, and it's going to get heated up, and it's going to go up because it decreases the density, and this is going to go around and around. And the critical reason, this is still a density gradient. I got low to high density, but it's just oriented differently, and this is not stable. Okay. So I think you have one or two problems on hydrostatics, gravity for the homework, which we're going to be starting next week. We might do some review of the index notation, but I'm going to consider everyone knows it by now. Unless you come to office hours, then you can ask as you like. All right. So the hydrostatic equations are pretty simple, right? You basically just have you just have pressure and density and gravity. All right, now we have to introduce, now we get to so Newton actually worked on fluid mechanics. You never wonder why they call it a Newtonian fluid? It's because of Newton. I gotta work on that joke. But basically, we're gonna show. So okay, this is what we're gonna show today. All right. So in general, so that was hydrostatics. Fluid in motion. It's not that simple. I mean, it's crazy. Like all these journals of fluid mechanics in the library, we're all just trying to solve one equation, this Navier-Stokes equation. So in general, for fluid in motion, Newton and a couple other people said, okay, you have your basic hydrostatics, which is you have your pressure, which is an equation of state, which depends on time and position. But then you have this thing called the deviatoric stress tensor. That's a new word for us, deviatoric stress tensor. Also with 9 components. T has 9 components. This is just called the regular stress tensor. I guess they call it hydrodynamic stress tensor. Okay, so we have our this is basically the pressures from the static case and actually if you want to be really rigorous, it's not obvious that this P is going to be the same for the static case as the dynamic case, but that would be like graduate class level 2. I'm going to talk about that. But there's some discussions in books how they go from that. And if someone wants to talk about it as a course project, it's not bad. People argue this deviatoric stress tensor, what could it depend on? Well, if P is including all the static fluid, then this deviatoric stress tensor, they call it deviatoric because it's like you want to take the word derivative and make it into an adjective, and they just made it into that. So it involves derivatives, spatial derivatives of velocity. But as we know from doing homework 1, del U, so you remember U, all right, let's talk about this. U has 3 components, U1, let's get to the real world so we're not confused. Ux, Uy, Uz, right? 3 independent velocities, which we're going, and each of these is going to be a function of x, y, z, and time. So because there are 3 independent velocities, and each velocity is a function of 3 different coordinates, this del U also has 9 different symbols, 9 different possible values for each of those 3. So del u is a tensor with 9 values. 9 values. All right. And we learned that del u is del u is not del dot u, it's del u, gradient of u. Oops, sorry. All right, so this is like the philosophical point of like, okay, so we know it has the fluid velocities in there, and we think it has, and this is what Newton said. Newton said it should depend on the derivative of the velocities. I think they said that because like, hey, we don't know what else to do, so let's just assume it's going to go as a derivative. And well, it turned out that he was right, or that's a pretty good notation for the Newtonian fluids. All right, so to make progress, they recognize that fluid flow can be separated into 2 types. One's called strain, and the other one's called rotation. And mathematically, we can write that as the following. So del u is equal to 1/2 del u plus del u transpose. After homework 1, you should be comfortable with the transpose. It just takes the matrix, transposes the off-diagonal elements, plus 1/2 del u minus del u transpose. All right. So all I did was take del u, added this transpose and subtracted it, and multiply 1/2, so it would be nice, and just give us what I needed to, right? I haven't done anything special. It's just algebra. So we're going to be talking about these a lot. This first one is called E, the rate of strain tensor. Hold on. First, let's even go back. So this is called the symmetric part, because clearly if I add the transpose to it, the top and bottom diagonals are going to be the same, right? I've just added the transpose, so they're, and this is anti-symmetric, which means they're definitely not the same because I subtracted the symmetric parts off. Okay, and this one's called E, and this one's called omega. This is the rate of strain tensor. This will be your friend to do the bathtub problem where you spin your hand and measure how long it takes to boil yourself from spinning your hand and heating up the water by viscosity. Rate of strain tensor. Again, everything's 9 components because we started with 9 components and we're going to have, and just stick with 9 components. And this is omega, and it's called the vorticity or the rotation tensor. We're not going to do too much vorticity in this class. There's a whole textbooks on graduate vorticity. There's things called Ekman boundary layers and things like that. Really weird, unexpected things that happen that are very non-intuitive. And the key part, this one involves no rotation. So no deformation, right? Because if I rotate it, I'm not deforming it. I'm just basically like spinning the whole thing. Every particle is in the same relative position as every other particle. Because it involves no deformation, this can generate no stress. That's a key point. So we started with, Newton said, hey, I bet the stress is a function of the derivatives of u. And let's separate the derivatives of u into the symmetric parts and anti-symmetric parts, which pertain physically to strain, which is like pulling stuff out. And we'll do a problem with that with basically uniform expansion, which they call dilation, and spin. And the spin generates no stress because it has no deformation. Therefore, for the rest of this, we're basically just going to assume we're going to just use E and ignore omega. All right, let's draw some pictures here and talk about physically how we're going to use these things. All right. All right, so let's consider, basically, we've got this point, this x naught vector.
What does that last word say next to x naught?
Indicate. Oh, man. All right, so let's say we've got this. We'll just consider non-time dependent flows for now. This velocity vector at x naught, and we define this basically small deviation delta x. And we have this new position, x naught plus delta x, here. So we're considering these 2 points. And this is supposed to be a velocity. All right. Taylor expansion tells us we can write we can say the velocity at a point that's sort of a distance away from us, you consider that to be in the future, is basically the velocity where you were originally plus how much the velocity has changed over that increment delta x. And because we're in grad school, we're going to do the gradient of u, which is how it changes in all 3 directions added together. Okay. And then plus any, and the delta, and the Taylor expansion also has second order terms. We're not going to talk about those. All right. Well, what we learned about, we can split del u into the 2 components. We can also write that as u of x naught. Remember, u is a vector, x naught is a vector. We can write that as the sum of the rotation components and the strain components. Okay. So you're going to have, imagine you have a fluid just spinning without deforming. You just have that omega term. If you have a fluid that's in a Couette flow that's straining without rotating, then you have the second term. So let's draw this pictorially. We call this a superposition of 3 types of flows. Okay. So we could have our original uniform flow, which is what we had before. Like if you're already at uniform flow and you don't change anything, you're going to keep on doing that. So this is uniform flow. You could also consider this to be solid body translation. Like if I don't know, like the whole Earth's ocean is rotating, or I take an aquarium and I put it in a car, there's no relative flow between the aquarium molecules, but the whole aquarium's moving. Okay, then I could basically spin this thing, and this is solid body rotation as opposed to translation. Like I could put on a record player. This is omega dot delta x. And lastly, I could strain it. And I'll denote that kind of like this, where I basically kind of like maybe pull it like a chewing gum between 2 sides. And this is going to be E delta x. Pure straining flow. So all flows can be written as a sum of these three things. And because rotation does not involve deformation, only straining flow contributes to tau, the deviatoric stress. So we now tau and E. Any questions? Any questions so far? Yeah.
What is right on the right out of the board? Pure strain.
Pure straining flow. Like these are uniform flow, solid body rotation, and straining flow. Yeah.
So we're kind of just ignoring solid body rotation and uniform flow, or
Well, because they don't generate deformation. To get deformation, you got to have fluid particles moving relative to each other. Each of those are basically just translation or rotation, solid body, as in the whole relative particles relative to each other don't change.
okay, so all this would this all be valid if it was rotating and we just like put ourselves in that rotating frame, or would that get weird really fast?
If it's a solid rotating as a solid body, it won't generate any stress. Like if I take an aquarium and I spin on a record player and I come back in an hour, the whole thing will be at steady state, and it's going to be like it's a block of ice. Then you don't have any extra deformation. But if I do other kind of vortices, like there's different kind of vortices where basically you could generate some stress, then you could have straining flow. Any other questions? Oh, yeah. Uh-huh. Deviatoric?
No,
We now relate. We now relate. Okay. Let's talk about Newtonian fluids. Why is my handwriting so bad? Let me reduce this. All right, there are three big ideas for Newtonian fluids. It's linear and isotropic, and the relationship is instantaneous. So let's talk about those. So the relationship between the stress and this strain rate is local in space and time. So that's just a fancy word for instantaneous. And you think of fluids that basically don't satisfy that, they have memory. Like any household products you know that has memory, that's a fluid. Eating edible products. Like peanut butter. You know, if you ever open a can of, not a can of, what are the plastic things of peanut butter? A jar, yeah. And you basically say, oh, someone left some bread in here. Or like, oh, that's somebody's spoon. And that was definitely not instantaneous. That was left like probably, weeks ago. So that's an example because peanut butter has these polymer chains that can maintain static stresses. Fluids should go to the shape of their container and they shouldn't remember stuff. They should just basically, whatever you do to them, they should respond instantaneously and shouldn't keep the memories. So Newtonian fluids are not like peanut butter. They're instantaneous. So counterexample fluid with memory. Like polymer. Does anyone work in like the oil industry before? I know we have gas industry, but like oil industry. Anyone have a rheometer? Rheometer is like something that measures viscosity. Basically, any kind of food product that you've eaten, like yogurt, has probably been through a rheometer, chocolate. And what they do, before they do experiments with it, they do this thing called a pre-strain. They just spin it over and over. It looks like a record player until like any kind of memory, hopefully, has been extinguished. It's like taking Etch-a-Sketch and just shaking it. All right. The next idea about Newtonian fluids is that they're linear. Okay. You remember back in linear meant y equals mx back in like high school. Now the issue is that E has 9 components. And if we want to relate something with 9 components to something else that relates 9 components, you need to multiply by something that has 81 components. 1, 2, 3, 4. So that's basically the grad school version of y equals mx. This 1, 2, 3, 4. A is a 4th order constant tensor. So the thing about it, basically, tau has stresses like tau 1, 2 stresses on the one face in the 2 direction. This is saying each stress could be a function of all 9 strain components, because I have no idea which strain component to use. So each one of my 9 things could have a function of like any of the rate of strain in any of those 9 directions. And if I do that for all the strain components, that's why I got 81. So that's why A has 81 components.
Is that a double dot in between?
Yeah, it still is a double dot because this is a 4th order multiplied by 2nd order. There's going to be 2 unit vectors left, and I'm gonna write this in index notation in a second. So 4th order constant tensor. All right, so in index notation, tau ij, remember the stress on the ith face in the jth direction, there's 9 different possibilities, is going to be equal to A ij kl times E kl. E, remember, has 9 components. And like we said, we say this because we say each stress component is related to all 9 components of EKL. So like I said, I don't know what direction I'm going to take, so I have to take all of them. And that means A, 1, 2, 3, 4, has 81 components, right? Don't worry, we're not going to do much stuff with A. We're going to be sticking to 9 but this is you have to understand where this all comes from. So it turns out A has some special properties, and we're going to manipulate. So Newtonian fluids have one more property, and that's the fluid is isotropic. What does isotropic mean?
Doesn't change with direction.
Yeah, no preferred orientation. In space. So that means the fluid doesn't have a head or a tail. It doesn't care if it's upside down or whatever. It basically can do whatever. It doesn't know what is a direction. And if you've got like there's fluids that have an orientation, like if you look at swarms of bacteria. So counterexample. Bacteria. They consider so bacteria is often rod-shaped. Then there's tend to be more flow in certain directions than others. A lot of these fluid flow models are used to measure model traffic and things like that. Cars are not spherical either. But luckily, all the molecules that we care about for Newtonian fluids are like small enough that their direction doesn't matter. Class ends in 10 minutes and 10:45, right? Do people want to talk about the homework the last 10 minutes? Okay, I see some nodding. Usually, Cedric, this is your first class. Usually we'll have the course project presentation, then we'll have the material, and then we'll try to do some catch up with the homework. What question do people want to talk about on the homework? And we're talking about homework 1, because that is due in 4 days. Thanks. Anyone have any questions? Yeah? Okay, 6-2. All right, so this is basically if I were really organized, I should just put this in the office hours, but let's just organized. It's fine. So recitation. So we're talking about number 6, 2. All right. We talked about this online yesterday, but let's go through it now briefly. All right, so you're supposed to show this, where basically I've got this surface area S, V is the volume bounded by S, and A is some constant vector. I don't know. A. A doesn't depend on anything. And X is a position vector. All right, so you got to do 2 things. I guess the big thing that shouts out to you is that you got to use the generalized divergence theorem. Let's just call it divergence theorem. Because to relate, divergence theorem helps you relate 2 things. You relates S to C. That's the 2D version. Basically, it relates areas to contact lines, and it relates S to volumes. Okay, and divergence theorem goes from basically a flux. Here, in some ways, you have a flux and a divergence. All right. And there's a generalized divergence theorem in the notes that says that we can actually be really, really liberal with stuff. So on page 80 of the notes, it says the following. It says basically, okay, it says this, where basically phi is any quantity. Phi can be a scalar vector or a vector, and star can be dot product, scalar product, which is just multiplication, dot product between vectors, cross product, extra. They say that makes sense. Like you can't start a sentence without finishing. So basically, for example, in this case above, you're going to do. You have to translate. I want to put the whole thing up. We have to basically make this in the form so that ends in the front. So what I would do if I were you we basically switch the order. ds. So we switch the order so it ends in the front, just like in this example. You can switch the order one more time of the inner one so that we get rid of that sign. Okay, ds. Okay. Because again, you switch the cross product, you get a negative sign. You switch the inside card, you get a negative sign. And this, you're going to use this generalized divergence theorem. You're going to say this is going to equal the divergence of A cross X dv. And this is as far as the vector manipulation can take you. No, you can take it. I would say you can do it one more step. So here, for your own sakes, yeah, do not. Index notation is very confusing, and there's very easy to make errors. It's impossible to basically check if you make an error. So I would try to stay in the vector notation world for as long as possible. That means applying some of these identities. And the identity, one of the identities we have, let's see, cross product of the divergence, the curl of a cross product. So we have 4.5, which says to split this into 4 terms, equals integral of 4 terms. I would do it like that. Does that help? Okay. And once you do those 4 terms, then you can figure out which ones are 0. And then for the remaining terms, you can do the index notation. Okay. All right. We got time for one more question.
I don't know how to put it in a question. I'm having trouble with problem 7. I can get to the point where I can pull out the so we set up in a condition where we said that basically the material derivative of rho is 0.
You need to use incompressibility for this. Wait, is that true?
Well, yeah, because you get a point where you can say that dp dt or d rho dt plus what do you call it, the divergence
Yeah.
of rho u is equal to 0.
Yeah. Yeah.
So I can get to that part.
Well, I think that's conservation of mass. That's not incompressibility. That's just conservation of
No,
mass.
you're right. That's conservation of mass.
Yeah.
But I end up with an extra term, and I can't figure out how to prove that that's 0.
All right, so part number 7. So number 7, basically, you're supposed to show this. So we're given Reynolds transport theorem, RTT, which is fx of t dv is equal to dv. So that's Reynolds transport theorem. And then this one, you're supposed to work with a special formula around Reynolds transports. Prove. So the goal of this problem is to prove this. D of dt rho g of x of t dv is equal to rho dg dt. So you're supposed to have this term on the right remaining, v of t. And I would start by, you're going to set f is equal to rho g, x of t. So I would start with a regular Reynolds transport theorem. You start with this, you're going to plug it into here, and you're going to put into here and here. So if you do that, it should start with something like this: d dt rho g x of t, v of t, dv. So just substituting in rho g plus del dot u rho g. So here you should get two terms, which we can just do it together because it's just product rule dp dt g plus rho dg dt. And this one you should also get two terms by keeping rho g together as a scalar function. So you're going to get del dot u times rho g plus u dot rho g. Okay. So you need so you're basically going to have four terms. Two of them are going to be 0, and then two of them are going to be non-zero. And then eventually this should equal to rho dg dt. Sorry, that's the end of class. But I will stick around. The new class is going to start rolling in here in a few minutes, but we can stick around to answer questions. And all of you that are still working on this homework 1, I heard there's a big group. Who's working on homework 1 right after this lecture? Don? What's your name? Felix? Yeah, you guys. But people get each other's contacts and group me. It's coming down to the last days. You don't want to be on like Sunday night, be like sending the group me, hey, can anyone help me with number 1? Because everyone's gonna be like, hey, I spent 3 weeks on this. I'm not going to respond. So please, help each other today. Do it as a group today, and let's get it in on Friday, and with minimizing the number of late submissions. Remember, it's 1% per hour that it's late. So every day you're going to lose 25%. 24%. Yeah.
And the homework is due like on Friday morning?
Midnight. Yeah, midnight.
Every second counts.
What?
Because when I checked,
Oh, I might have made a mistake. I'll change it to. I think I made it Wednesday because I was optimistic. I thought people would submit it, but then I'll move it to Friday midnight, 11 p.m. Okay, I can change it. Don't worry, I'll change it.
I think I see where it went wrong. So that's u dot del rho g. I expanded that out to u dot rho del g plus u dot g del rho. That's where my extra term came from.
This should be spanned out until. Oh yeah, I'll do that.